All right, good evening. Welcome to our January public event, the first one of 2025. My name is Kareem Jaffer. I'm the public events coordinator for the Royal Astronomical Society of Canada's Montreal Centre. And we are really happy to have with us an incredible speaker for tonight. But before we get to that, we always start our Montreal Centre public events with a land and sky acknowledgement. At John Abbott, we always acknowledge that we are on unceded Indigenous lands here in the Montreal area. But with the RASC Montreal, we also acknowledge that we share the night sky and all of the observations that we make with not just the First Nations, but also ancient cultures from across the world. And there's no better place to look at that but with the monthly moon. And right now, if you look out at night, even with the clouds, the moon is brilliant shining through the clouds, as are several of the planets. Tonight, after sunset, you could see Venus shining through the really thick clouds, still visible to us as we drove westward. And when we look at the moon and we see the moon becoming larger and larger with this waxing moon, aiming towards full moon in just a couple of days, what we are looking at is a moon that the settlers always called the wolf moon, because at this time of the winter, the wolves would be hungry at night, the nights would be long, and the howl of the wolf would be very, very clearly visible on those cold nights. The First Nations tend to recall the moon more with what's happening in nature or where they are through their journey through the winter. So many of us remember from the wonderful works that we read back in high school, Gitchimanzu, the idea of the spirit moon, which is captured by the Ojibwe. Or the Cree. I actually love the Cree for the January moon because they call it the trees exploding moon, because you can hear with the maple syrup and the sap of the trees freezing and then thawing and then freezing and then thawing, the crackling of those trees. And so those observations allow us to remember that we're not the first ones to look up at any of these phenomena, whether it's planets all being clear on the elliptical as we're going to, on the ecliptic, as we're going to be seeing over the next few weeks, or whether it's something as simple as seeing the moon in the early morning before it sets and getting a chance to enjoy the moon for a few moments on your way to work. So we try to make sure that we have that connection before we go into any of our public talks. We're also very, very honored at the Montreal Centre that our honorary president, David Levy, is able to join us often. And David Levy right now is in Arizona. So David, I'm gonna ask you to give us a welcome, please.
Thank you, Kareem. Can you hear me?
Yes.
Great, okay. I am really looking forward to this lecture tonight. I'm all comfortable and ready to start and ready to enjoy this lecture. You get better and better lectures all the time at the Montreal Centre, which happens to be my very favorite astronomy club. It is the first one I joined. I joined it back in 1964, although my first meeting there was October the 8th, 1960. I met Isabel Williamson that night, Constantine Papakosmas, Kenneth Chalk, and a lot of really historic people in our Montreal Centre. I'm going to read you a little welcome poem that should be appropriate for a lecture on how to find a planet that is capable of supporting life. And I'm taking it from Tennyson, who I think would have been really excited about listening to a lecture. And if he were still alive, he'd probably be here and he'd be as excited as I am listening to this lecture. And it's the end of his poem, Ulysses. And it goes like this. The lights begin to twinkle from the rocks. The long day wanes. The slow moon climbs. The deep moans round with many voices. Come, my friends, 'tis not too late to seek a newer world. Push off, and sitting well in order, smite the sounding furrows. For my purpose holds to sail beyond the sunset and the baths of all the western stars until I die. It may be that the gulfs will wash us down. It may be that we shall touch the happy isles and see the great Achilles whom we knew. Though much is taken, much abides. And though we are not now that strength which in old days moved earth and heaven, that which we are, we are. one equal temper of heroic hearts, made weak by time and fate, but strong in will to strive, to seek, to find, and not to yield. Thank you, and back to you, Kareem. Thank you.
Thank you very much, David. And for those of you who want to hear a little bit more of not just David's poetry, but also some of his recollections and reflections on observing, this coming Tuesday night will be the next Global Star Party on YouTube. If you search for Explore Scientific or Global Star Party, you'll see it live. David is on there with Scott Roberts from Explore Scientific and astronomers, researchers, and educators from across the world. And so this Tuesday is, what number Global Star Party is this now, David?
I think it's 162 or something like that. Or
162. He has been on 162 of these Global Star Parties that range between 4 hours to, I think the longest one you did was 26 hours, right?
Yeah.
Yeah.
I'm still alive.
People sharing their joy of astronomy from all different backgrounds, all different walks of life. Wonderful. Thank you so much, David.
Thank you.
So now it's my pleasure to introduce our current president, Maury Portnoff, who's going to speak to you a little bit about what the RASC is and what the Montreal Center is.
Okay. Going? Okay. I'll stand here so I can read it with my glasses. It's hard. I want to welcome everybody here who took the time to come out tonight where I talk with Dr. Wong. I'm sure it's going to be very interesting. And I also want to welcome all the people on Zoom out there. And I have to do something, bear with me. I invited my son to come online. I don't know if he's there.
He's there.
He's there? Okay. Well, my son Bruce, he's an aerospace engineer working at Johns Hopkins University, the Applied Physics Lab. So I'm, as a proud father, I just want to say welcome. And one day I'm going to get him to come here and give a talk, guaranteed. So welcome here. We're the Montreal Center, and we're part of the Royal Astronomical Society of Canada, which was founded in 1868, quite a while ago. And there's over 4,000 amateur, educator, professional members who are members, and we're the largest active astronomy group in Canada. And basically, our mandate is to inspire the curiosity of Canadians and beyond, and to share the knowledge and what they see in the night sky.
No, the keyboard down there.
Oh, okay. The Montreal Center is just over 100 years. Founded in 1918. We're one of the oldest centers in Canada. And we're probably the most active center in Canada, I'm proud to say, particularly during those cold period, the COVID period. You all remember that? Our activity skyrocketed. We were active, I don't know how many times a week, but we were always online with Zoom. We rediscovered ourselves. We branded ourselves on Zoom, and we haven't stopped. So, and that was great. I mean, COVID wasn't great, but what we did was great because we were able to get speakers from all over the world giving us talks that would not be able to come here normally. So it was fantastic for that. It was also great for introverts. It was a fantastic period of time for if you're an introvert. You didn't have to be embarrassed about staying home. Loved it. Okay, the Montreal Center, we have a long-standing relationship with John Abbott College and McGill and the Arboretum. We have an observatory, the Morgan Arboretum, a 14-inch mead. We also have a dark sky site near the US border, and we call it Woolly Woods, where we have a 16-inch light bucket and other telescopes, more coming. It's a wonderful place. If you're a member, you haven't been there, please go there. If you don't have a telescope, just come out there, bring a lawn chair and look up, it's an amazing sky to enjoy, just amazing. And we have observing events, workshops. In fact, we have some astrophotography workshops coming up, which are well attended. We have clubhouses. The large part of the Montreal Center is social. Yes, we like to do astronomy, but we're a very social, friendly group. And we have members of all different levels. If you're a beginner, no problem. If you don't have a telescope, even better, because our members love to share their telescopes. You have questions, we love to answer them. If we don't know the answer, we'll make it up. You don't know the difference? It's great. No, seriously, we're a very friendly group. If you don't know something, no one's ever told me, go read the manual. I've been in other groups and the first thing they say is go read the manual. We don't say that. We'll help you. As long as it takes. We have a lot of patience. We just like helping our members and the public. We have clubhouses. Those are very informal events. We don't know what's going to happen at a clubhouse. Members bring new pieces of equipment, projects they're working on. They may give an impromptu presentation. We have movie nights coming up where we have real movie snacks without the movie theater prices, which is nice. In here we have also a library, which has a very good collection of books where members can take them out. We have some equipment that members can borrow. So we have an choice annually a swap sale where members can sell and buy equipment because you can never have enough equipment. So I've been told. There used to be a magazine, and we have some there called Sky News that was put out by National. However, that stopped publication a couple of years ago. But we have our own journal called Skyward, and because of that, it's now being distributed across Canada, and it's an amazing publication. It looks like it is a magazine, but our members and others contribute to it. So if you have an interest in writing something, by all means submit it. It'll be accepted, guaranteed. If you're an artist, we like images, posts, pictures, whatever. It's a wonderful publication. It's seen by around Canada and beyond. We have monthly public talks, star parties, different events. We do outreach to local groups like Scouts, Girl Guides, different libraries around Montreal, Beaconsfield. Some of our events was such as the comet that was just recently, auroras. If it's a clear night, we're out there, and everybody's welcome to join us. So with that, I'll call to Karim again, and he'll talk about upcoming events.
Thank you, Maury.
Yep.
As Maury mentioned, our members events are open to members. They're also open to the students at John Abbott College through our partnership, so that the students get a chance to experience a little bit of the amateur side of astronomy without having to become members while they're still dealing with their school and everything like that. And we often have alumni come in who are currently studying at Concordia or McGill, Bishops, University of Montreal, sometimes Purdue. They just pop in sometimes and join us in the middle of the. So our upcoming members events, we're actually starting a series of astrophotography workshops beginning later this month and happening every month for the next 4 months to get us through the winter series. So even if you're a new member or you're a longtime member, getting a chance to see astrophotography done by different people with different equipment and different approaches lets everybody learn from each other's skills. So if you're considering a membership and you haven't become a member yet, this is a great time because it gives you those 4 months of hands-on workshops to begin the series. We also have these monthly library nights, and we're going to be starting them off for the 2025 year in February with a really special guest. One of our members, who's also a member of the Dorval Club, Gilbert Saint-Onge, he won one of the King Charles III coronation medals for his work in Quebec astronomy for the last 60 plus years. And how active he is, I'll tell you, every couple of months, myself and our Skyward editor, Gerald, get an email, a new research article that he's put together for the French Society that he translates and asks us to double check before he submits it to our RASC journal, which is the academic side of RASC, the ones who do the actual astronomy and science together. And so he still continues to publish now. 60 years after he began his astronomy, he's an active researcher. So we're going to be doing a library night with him and then followed up by just perusing our collection. And then we also have, starting this month, at the end of the month, an overview of what's going to be visible in the night sky for the next month. So the things to look out for, any specific conjunctions or events that you want to try to capture. And our members liaison, Nicole, is going to be giving those on Zoom so that any of our members can comfortably attend those without having to leave, or even if the bridge ends up closed across the way. Our By the way, the astrophotography workshops that I told you about, David here is organizing them. He's also organizing movie nights. So those will be happening monthly as well. And the movie nights, or actually more than monthly, right?
The 25th is our first movie
Yeah,
night.
Saturday, the 25th is the first movie night. And the movies are not like, you know, sitting and watching a documentary on the block, although that might happen, but it's going to be really, really old geeky sci-fi stuff. So today's talk by Mike and some of his extracurriculars will set us up nicely for that as well. Our public events, as Maury said, we try to do them at least monthly. This month we have our in-person event, and we also have an annual live stream that we do with Guelph Physics. Guelph, Ontario, their physics department joins with us, and we give them content for their monthly stargazing guide. And then we have an annual co-hosted event where their students and our students at John Abbott and at University of Guelph moderate the Q&A while we get a researcher and we alternate back and forth. So last year we had Emily giving a talk on some of the work she's been doing on analog missions, on different types of space environments and getting people attuned to what they would experience there. So this year is going to be one of the Guelph researchers who's going to be giving a presentation for us. In February, we're going to have a mobile planetarium here at John Abbott, hosted by RASC Montreal, featuring Plateau Astro, who's one of our outreach colleagues from the middle of Montreal. And he's going to be doing a mobile planetarium show, and he's going to be doing several different iterations of it. So we'll have sign-up sheets starting in start of February with time slots so that you can book your time to go into the planetarium show. And then outside of the planetarium show, we'll have another conversation area going. And then in March, we have two things happening. We have a beautiful lunar eclipse happening starting at around midnight. So we'll be starting late night on a Thursday, ending early Friday morning. So we'll be doing it here at John Abbott on the Oval if weather allows. And then we're also doing an Earth Hour event, which is the day that we try to shut the lights off for an hour to remind ourselves what the night sky looks like in Montreal, because we kind of forget sometimes. So we're hoping to do something to highlight a little bit of light pollution abatement. But for tonight, let's jump right to our wonderful keynote. And to introduce our speaker, we have one of our alumni, Emily Laflèche, who's visiting us from Purdue, where she's also pursuing astrobiology. Now, if you want to know more about what Emily does, you can find 3 of her talks now, I think, that have been put up on our YouTube channel, including our Townsend lecture from a couple of years ago, which is our keynote public lecture of the year. But she reached out to me with this idea to bring Mike in as a speaker, because Mike is giving a science talk at McGill in a couple of days. And so he was willing to come in early to come and speak with us. So I'll let Emily introduce Mike. Emily?
Hello, everybody. I am so happy to be here and to be back in basically the place where my career started, I like to say. I'm so happy to see all of your faces again and also some new faces as well. And today I have the great, immense honor of presenting one of my dear friends and collaborators, Mike Wong. He did his undergrad at UC Berkeley in atmospheric science and then pursued a PhD at Caltech in planetary science. He is currently a NASA Sagan Postdoctoral Fellow, which is a really big deal fellowship, at the Carnegie Institute for Science in Washington, DC, where he does basically every kind of research project you can imagine in the field of astrobiology. We collaborate on many different projects together, which I will not get into too much because I know he's going to be chatting about them today. But he is truly someone who cares not only about his science, but also about others. And he does this through mentoring many students, both in high school, undergrad, and even grad students like myself. He really just makes sure that everyone feels included in STEM. And for that, I think he is one of the most incredible people in our field. So I am so lucky to know him as a person and to present him to all of you, my RASC family. So please give a great round of applause to Mike.
All right, let's see if I can navigate this correctly. So I need to share my screen. Boom. There we go. Let's press play. Okay. Actually, wait, before I do that, let me close this. Okay. Good. All right. Well, thanks, Emily, for that wonderful introduction. And it's such an honor to be here at RASC to share a little bit of what I like thinking about. So as Emily mentioned, I'm an astrobiologist. And one of the most frequent questions that I get as an astrobiologist is, how can you even do astrobiology? Because you haven't discovered life in the universe yet. And that's a fair question. And my answer is, but we have discovered life in the universe. People do that. Their eyes widen, they gasp, their jaws drop to the floor. They wait in bated anticipation for me to reveal some government secret about where we're keeping the alien bodies. And then I just remind them that you're life in the universe. I'm life in the universe. We're all life in the universe. You see, the moment that we discovered that our entire biosphere rests on the thin shell of a rocky planet that orbits a star, one of 200 billion stars in the Milky Way galaxy, one of 1 trillion galaxies in the observable universe, we discovered life in space. And the exciting question that we astrobiologists get to ask now is there more life in space out there? Now, this is a question that the ancient peoples of the earth could not even fathom asking. They couldn't even cross their mind because they saw different things in the night sky. And I don't just mean that they didn't have to, contend with light pollution. I mean that they interpreted what they were seeing in the sky differently from how we do today. So for example, the word planet means wanderer, right? Because of the way that planets wander across the fixed backdrop of stars as you observe them night after night. This is the trajectory that planet Mars traces out in the night sky. Today, we all have this intuitive feeling. We know Mars is another terrestrial planet out there that you could send a rover to go visit, or that you could even imagine yourself sinking your boots into one day. But the ancient peoples, they didn't have that conception. All they saw was this pinprick of light tracing out some kind of trajectory in the sky, going this way, and then deciding, actually, wait a minute, I don't want to go that way, going back, and then deciding, wait, actually, that was the right direction after. So the ancient peoples of the earth thought of planets not as places that you could go, but as spirits that you could know. So, for example, the ancient Babylonians were one of the first people to make rigorous astronomical observations of the night sky. And they also worshipped this god Nabu, who was their god of literacy, rationality, writing, and wisdom, essentially their god of science. And they identified Nabu with the planet that we now know and love as Mercury. Another great example from history is the writings of the great Greek philosopher Aristotle. Aristotle was one of the first people to try to develop coherent theories of motion and matter. In Aristotle's world, everything you see around you was composed of 4 elements, right? Earth, water, fire, and air. And that weird motion of the planets puzzled him. And so if you go back to Aristotle's writings, you'll see that he conjectured that planets were either living entities because only living things could move of their own accord, or that they were composed of an ethereal 5th element that he called quintessence, something that didn't exist here on Earth, only in the celestial heavens. And so it's clear that the way that ancient peoples understood themselves and their place in the universe was due in part to the way that they interpreted the night sky. For millennia, people thought that we existed in a geocentric universe, right? Where we're all at the center of the universe. We're all the center of attention. The moon, of course, orbits the Earth, but so does Mercury and Venus. And there goes the sun orbiting the Earth as well, followed by Mars, Jupiter, Saturn, and the great firmament of stars beyond. But then something happened, which is that people developed telescopes, and they started pointing telescopes at the night sky. And famously, Galileo looked at Venus and saw that Venus wasn't just a pinprick of light. It had shapes to it that changed observation after observation. He saw the phases of Venus, which were inconsistent with a model where everything orbited the Earth. Galileo also pointed his telescope at the surface of the moon, and he observed that the moon's surface was rugged and chaotic, which was inconsistent with the idea that the moon was this perfect heavenly body. And then most famously, Galileo looked at Jupiter through his telescope and discovered what we now call in his honor the 4 Galilean satellites, the largest moons of Jupiter: Io, Europa, Callisto, and Ganymede. And to him, they were just pinpricks of light, but clearly they orbited a different body out in space, not the Earth. And that went completely against doctrine. It was a long and torturous road, but eventually scientific observations won out, and we revised our view of the solar system to have a heliocentric model with the sun at the center, and Earth is just one of many planetary bodies that orbit the sun. And this is the picture of the solar system that we all learn in school today. Again, Earth is just one of many different planetary bodies, all orbiting this incandescent ball of gas. So revolutions in astronomy like this are due in large part to revolutions and advancements in telescopic technology. Galileo's telescopes were very rudimentary. Right? In the 1600s, he had basically 2-inch diameter telescopes. School children make these types of telescopes today. I'm pretty sure this celestron right here is way more powerful than whatever Galileo had. And yet, it revolutionized our view of our solar system. In the 1920s, the 100-inch Hooker telescope at the top of Mount Wilson in California revised our understanding of the entire cosmos by observing extragalactic phenomena and measuring how distant galaxies were receding from us, showing that the universe was actually expanding, which meant that it had a very different beginning from where it's going to end up, and completely revised our concept of time. And today, the 6.5 meter James Webb Space Telescope, or JWST, is revising our knowledge of the cosmos left and right. And I'll show you some JWST data later tonight. So historians have given a term to what's going on here. Historians of science say that astronomy gives us new technologies of perception that revolutionize human understanding, where a technology of perception is some device, contraption, or instrument that allows us to see farther or deeper than ever before, and forces us to revise the way that we perceive ourselves in the natural world. Now, these technologies of perception have this incredible ability to reshape how an entire culture understands its place in the universe. But it also has this powerful, profound ability to revise the way a single individual understands himself or herself or themselves on Earth. I had such a personal experience on one of my college astrophysics class field trips to Lick Observatory on Mount Hamilton in California. The next couple of slides are going to show you some images that I actually took that night on that class field trip. This is the entrance to Lick Observatory. That night, we had the great opportunity of being able to visit and look through the Great Lick Refractor. I just want you to look at this image and appreciate what a marvel this contraption is, how big it is compared to our docent. Even the dome itself is a work of art. This telescope was built in the late 1800s, and when it was completed, it was the largest refracting telescope on Earth. It has a 36-inch diameter lens, it's over 16 meters long, and it weighs over 1,000 kilograms. And famously, it was the first telescope to discover a moon of Jupiter after Galileo discovered the 4 biggest ones in 1610. It discovered Amalthea. So what impressed me the most about this telescope was the way you had to slew it by hand. Remember, this telescope was built in the 1800s, so there weren't any automatic motors to get it to point where you wanted it to go. You literally had to run up to this telescope, grasp it with both arms and push it. And because it was so heavy, it would lift you off the ground and set you somewhere else in that magnificent dome. It was a whole science, art, and expertise to point this telescope where you wanted it to go. And it was a fateful night. It was a beautiful night. The silver glow of our moon was pouring through the windows. And one by one, our class went up to this historic telescope and viewed marvels of the night sky. We saw galaxies, star clusters, nebulae. But the thing that impressed me the most was this image. Looking through the telescope and seeing Jupiter and all 4 of its Galilean moons lined up. And if you could squint just a little bit, you would even see the marvelous bands of Jupiter's atmosphere, tumultuous physics in action. And I don't know what it was about that moment. It was just that realizing that there were photons of light bouncing off the atmosphere of Jupiter, bouncing off the surfaces of these icy moons, getting refracted through these telescopic lenses and then hitting my eyeballs, which just felt so powerful and so profound. I felt like Galileo himself at that telescope. And it really was a moment I'll remember forever, because this was the moment that I decided that I wanted to be a planetary scientist. So, as Emily mentioned, I went to UC Berkeley, decided to major in planetary science. And after I graduated, I went to Caltech, where I did my PhD in planetary science. After that, I went up the western coast of the United States to Seattle, Washington, where I did my first postdoc in the astronomy department and astrobiology program there. And 3 years ago, I moved across the country to Washington, D.C., where I'm now at the Carnegie Institution for Science as a postdoc in astrobiology and data science. Throughout my journey, at each stage, there was something that really helped propel me along. For instance, when I was an undergrad, between my sophomore and junior years of college, I did a 10-week internship at Carnegie, the place where I'm now employed today. During this internship, my job was to crush material between tips of diamonds and shoot them with lasers to simulate the high pressures and temperatures of Earth's deep interior, figure out how those materials behaved. And the biggest thing that I discovered in that internship was that I really hated doing that work. And I think this is such an important lesson. One of the biggest things you can learn as you're going through science is learning about what you like, and perhaps most importantly, what you don't like, so that you never have to do that again. In graduate school, one of my PhD advisors was a scientist at NASA's Jet Propulsion Laboratory, who was an expert in the origins of life. And this was my first foray into the field of astrobiology, thinking about how life could originate on the early Earth and on distant exoplanets and moons. During my postdoc at the University of Washington, I was introduced to an interdisciplinary and international collection of colleagues studying exoplanets. And at Carnegie, my funding actually comes from the NASA Hubble Fellowship Program, where I'm a Sagan Fellow, as Emily mentioned, which has really granted me an incredible amount of intellectual freedom to pursue the kind of science that I like in the way that I like doing it. And as a result, I've discovered that I don't hate all lab science. There is actually some lab science that I do enjoy, especially when it's connected to looking for life elsewhere in the universe. And it's also allowed me to do some of this really cross-cutting and exciting work that I'm collaborating with Emily on that I'll talk about later today. So I think if there is one piece of advice to give to the students in the audience, and I know there are plenty of astronomy students out here, it's that I hope that you all take the opportunity to explore while you're young in your early career. Because I really think that if I had not done this summer internship and been brave enough to move across the country to try something new between my sophomore and junior year of college, I honestly don't know if I would have the job that I have today, working at that very institution. But maybe I was destined all along to be a planetary scientist and astrobiologist, no matter what happened, because I cannot remember a time when I wasn't in love with Star Trek. It's been there throughout my entire life. This is me dressed up for Halloween as Captain Kirk when I was 6. And this is me 21 years later. You can't really see that, unfortunately, but this is me at my thesis defense, dressed up, defending my thesis in a blue science officer's uniform. So for those of you who aren't familiar with Star Trek, let me try to explain it like this. Gene Roddenberry, the creator of Star Trek, once said that Star Trek was an attempt to say that humanity will reach maturity and wisdom on the day that it begins not just to tolerate, but take a special delight in differences in ideas and differences in life forms. Because if we cannot learn to actually enjoy those small differences, to take a positive delight in those small differences between our own kind, right here on this planet, then we do not deserve to go out into space and meet the diversity that is almost certainly out there. And I think in the classic Star Trek series, this spirit of diversity was exemplified through the character of Uhura, who was played by the late great Nichelle Nichols, and was a competent linguist, engineer, and navigator sitting in a leadership position on the bridge of the Starship Enterprise. Remember, Star Trek first aired in the 1960s during a time of great civil unrest in the United States over racial tensions. And this was a time in which you could not see a woman of color in a non-menial role on American television, except in Star Trek. Nichelle Nichols, after Star Trek's run, actually went on to work for NASA to recruit women and people of color into the space agency to diversify NASA's workforce. And I really think that the diversity that I saw on screen in Star Trek really made sure that in my mind, there was a space where I knew that there was a path that I could take to become a space explorer too. Gene Roddenberry, the originator of Star Trek, knew that diversity was at the core of Star Trek from the very beginning, but he also wanted science to be at its core too. So much so that he wrote in his 1964 proposal to NBC Studios for the creation of Star Trek about an equation penned just a few years earlier by astrophysicist Frank Drake. So this is what Drake's equation actually looks like. Apologies for the blockage there, but it doesn't matter. I'll show it to you again on another slide and you can read it all. It's basically, this equation is a way of trying to organize our knowledge and our ignorance about the cosmos in an attempt to calculate the number of intelligent transmitting civilizations in our galaxy. The thing is, back in 1964, you couldn't just Google Drake's equation, right? Gene Roddenberry had no idea what Drake's equation actually looked like. So under the pressure of the studio to submit his proposal on time, he simply scribbled something random onto a piece of paper and sent it in. And luckily, the studio also had no idea what Drake's equation looked like, and Star Trek was approved. Now, many years later, Frank Drake, Professor Drake, was invited aboard Star Trek to scientifically advise one of the episodes of a later series. And when he was in the studio, he was shown this fake Drake equation that Gene Roddenberry had penned in his name. And when he saw it, he just burst into laughter. And he said, "Oh, Gene, don't you know that raising something to the first power is simply itself? Like, why would you even write that?" Okay, so here's what Drake's equation actually says. Again, it's trying to estimate the number of intelligent transmitting civilizations in our galaxy. So we're not able, unfortunately, tonight to go through each and every one of these terms in great detail. But suffice it to say that the last four terms here, those shown in red, are really difficult to estimate. These are numbers that we still have no idea what they are today. They deal with things like the probability of the emergence of life or the lifetime of transmitting civilizations. However, the first three numbers, those shown here in blue, are astrophysical quantities. These are numbers that we can actually try to observe, measure, estimate, quantify using the technologies of perception that we have today. So if you take just those first three numbers and you multiply them together, you get the number of Earth-like planets in the galaxy. That's the number of stars in our galaxy, multiplied by the fraction of those stars that have planets, multiplied by the number of Earth-like planets per planetary system. Now, Gene Roddenberry had no idea what this number was either. There was no way for him to know in the 1960s. But he did know that whatever this number ended up being, it was going to be huge, right? Because the number of stars in our galaxy is literally astronomical. So when you discover what this number is tonight, you have a choice to make. You have a choice about how you're going to feel about this number. Are you going to feel small because you're just one being on a tiny mote of dust floating in the vast cosmic void? Or are you going to feel large because you're connected to this grand evolving universe of ours and special? Because despite what might be out there, despite all those possibilities, there exists just one and only one of you. This was the kind of mathematical philosophizing that Dr. Leonard McCoy brought to his captain, Captain James Tiberius Kirk, played by Montreal's own William Shatner, in an episode of classic Star Trek called The Balance of Terror. In this episode, Captain Kirk is pitted against an equally formidable Romulan captain, And he's feeling the draining weight of Starship Command. He's second guessing his every move. He just wants a vacation. So Dr. McCoy comes to his captain to spur him back into action. And he does so by prescribing a very potent, though very peculiar kind of medicine. And that's the mathematical probabilities of the universe. Let's see what Dr. McCoy says. He says, in this galaxy, there's a mathematical probability of 3 million Earth-type planets. And in all the universe, 3 million galaxies like this. And in all of that, and perhaps more, only one of each of us. Don't destroy the one named Kirk. It's a very powerful scene in which Dr. McCoy claims that there are 3 million Earth-type planets in our galaxy. Let's see how right he was. Today, we know that there are some 200 billion stars in our Milky Way galaxy. That's not an exact figure. It's just an order of magnitude estimate, but it'll suffice for our purposes tonight. Thanks to the Kepler Space Telescope and the TESS telescope, two of humankind's greatest planet-finding machines, we now know that the fraction of stars that have planets is essentially 1. Every single star you see in the night sky, on average, has a planetary system going around it. And thanks to the hard work of astrophysicists around the globe, we now know that roughly 1 in 5, or 20% of those stars, has an Earth-sized planet orbiting in that star's Goldilocks zone. So if we multiply these three numbers together, we get something like 40 billion. Remember, a billion is 1,000 times more than a million. So Dr. McCoy was off in his estimate by a factor of over 10,000. Yikes! But it's okay, we'll forgive Bones. Because after all, he'd love to remind us, damn it, Jim, I'm a doctor, not an astrophysicist. So we believe that there could be billions of Earth-like planets in the Milky Way galaxy. How can we know for sure? This is where the field of exoplanet astronomy comes to the fore. What I'm showing you in this image, this video, is all of the planets that the Kepler Space Telescope discovered as if they were orbiting a single star. I show you this video not to hypnotize you into believing that exoplanet science is the coolest science ever, but to just impress upon you how many exoplanets we've found, nearly 6,000. So it's going to keep people like myself and Emily up all night for decades to come to try to understand if some subset of these planets contain evidence for life. So no exoplanet talk would be complete without a plot like this. It's a busy one, so let me walk you through what's going on. On the x-axis, we have the planetary period. That's the orbital period of the planets, basically how long their year lasts in units of Earth days. On the y-axis is the mass of exoplanets given in units of Jupiter masses. Every single point on this plot is a different exoplanet, some 5,600 exoplanets as of 29 March 2024. They are colored by their discovery method. And as you can see, most of the exoplanets that we've found have been discovered through radial velocity or transits. Radial velocity is when we notice the presence of an exoplanet because of the gravitational tug that it exerts on its host star. It makes the star wobble ever so slightly back and forth. And by noticing the star's wobble, we can determine that there's an exoplanet there. Transits is the method by which we're looking at a star and we see it periodically dimming because from our perspective, the exoplanet crosses in front of the face of the star and dims it, blocks out some of that starlight. Now, there are several important things to point out whenever showing a plot like this. The first is that our exoplanet discovery techniques are biased. Specifically, they are biased toward big, close-in planets. Those are the easiest exoplanets to find. And they are biased against small, far-out planets. So just because you don't see very many planets in this lower right-hand portion of the graph doesn't mean they're not there. It just means we haven't found them yet. And part of exoplanet astronomy is trying to push this diagonal boundary ever and ever farther toward the lower right-hand corner of this graph. But despite the fact that our survey is currently incomplete, we've still discovered an astonishing diversity of planets out there. The first exoplanets to be discovered are the so-called hot Jupiters. These are Jupiter-sized planets that are orbiting so close to their star that their atmospheres are scorching thousands of degrees. And in those atmospheres, what condenses isn't water vapor into water vapor clouds, but clouds made up of titanium oxides, vanadium oxides, aluminum oxides. These are things that make up gemstones here on Earth. We have a population of colder Jupiters, much like our own, an intermediate kind of planet made mostly of astrophysical ices or water. The closest orbiting rocky or terrestrial planets are likely lava worlds because at that distance, they're so hot that their entire crusts are likely molten into magma. And finally, we have our potentially temperate terrestrial planets, some of which may host signs of life, the kinds of planet that we are most interested in astrobiology. So how do we actually go about looking for signs of life on an exoplanet? Well, it all starts with the planet's atmosphere, because that's the most observable part of a distant exoplanet. And we can tell what's in a planet's atmosphere by the way that starlight interacts with that atmosphere. As light of different wavelengths or colors passes through that exoplanet's atmosphere, some will be absorbed while other wavelengths will be transmitted. This will depend on the specific molecules in that planet's atmosphere, whether or not those molecules actually absorb or block that wavelength of light. And so this allows us to make an observation of an exoplanet as it transits its host star at multiple different wavelengths at once. So in this animation, you're going to see three different observations, one at 1.8 microns, another at 2.1 microns, and the last one at 2.3 microns. These are different wavelengths or different colors of light that you're making the observation at. So as the planet passes in front of its star, it will actually look different sizes based on the wavelength of observation that you're making. So in this example here, when you're looking at 2.3 microns, the planet actually looks quite a bit bigger than when you were looking at those other wavelengths. This is because there's something in that exoplanet's atmosphere that is absorbing specifically at 2.3 microns, telling us about the constituents of the atmosphere. So here's that JWST data that I promised you at the beginning of the talk. Again, it's a complicated plot, so let me walk you through it slowly. On the x-axis is the wavelength of light that you're making that observation at, going from 3 microns all the way out to 5.5. The y-axis is the amount of light that that exoplanet blocks. So as you march from about 3 microns to about 4 microns, you see the size of the exoplanet doesn't change. It doesn't matter what wavelength you're looking at, the exoplanet is that size. Until you get to around 4.4 microns, and then boom, the exoplanet has grown in size. And this is the telltale fingerprint of carbon dioxide in that exoplanet's atmosphere. Now, carbon dioxide is a very important gas, right? Because it's one of those gases that life breathes in, plants do that, and life breathes out. We breathe out carbon dioxide. However, don't get too excited about the prospects of life on this planet. This planet, WASP 39b, is one of those hot Jupiters. And so it's unlikely to host any life as we know it. So we need to build a new technology of perception if we are going to try to make an observation like the one I just showed you of an Earth-sized exoplanet, an exoplanet far smaller than that hot Jupiter. And luckily, that technology of perception is being planned right now. And it has the appropriate name, the Habitable Worlds Observatory, or HWO. HWO is a telescope concept we want to build and then launch over the next few decades. Let me tell you a little bit about what we're planning. HWO, hopefully, will have a 6 to 8 meter mirror. It'll be equipped with a state-of-the-art coronagraph, which will help block out starlight so that you can more clearly see the light coming directly from that exoplanet. We wanted to have a wavelength coverage as wide as possible, from roughly 100 nanometers to 2,500 nanometers. That spans the entire UV, visible, and infrared ranges of the electromagnetic spectrum. You also notice this giant sun shield here. Why is that there? Well, we need to keep the telescope cool, because if it warms up even just a little bit, its own thermal energy will disrupt or create noise in the infrared observations. The main goal of HWO is to directly image and characterize roughly 25 potentially habitable exoplanets and search for life on all of them. So why do we have to go all the way from the ultraviolet through the visible to the infrared? It's because we want to get a full census of all of the different molecules that might be in that planet's atmosphere. So oxygen and ozone absorb in the UV and visible wavelengths, and water vapor, carbon dioxide, and methane absorb in the infrared. So this is the kind of wavelength coverage, this is the kind of spectrum, as we call it, that we want to be able to observe of a planet out there. We can only do that if we cover that entire wavelength range. So this is our dream, to try to get something like this with HWO. But until we launch that telescope, all potentially Earth-like planets, to us, look like this. Just blank cue balls in space. All we really know about any potential Earth-like planets is their mass, their radius, and something about their orbit. They're basically blank canvases on which we have to build their possibilities using our imaginations. So how do we do that? Basically, like science fiction authors, we run what-if experiments for all of these different planets. We say, what if this planet had a certain atmospheric state? What if it had a certain ocean continent distribution? We write our science fiction stories not in prose, but in computer code, importing into them the laws of physics, chemistry, and biology to simulate an exoplanet and assess it for its potential habitability, to get to know whether or not it can really be habitable, and if it is, what we would need to look for in order to identify that habitability and that life that might be on it. Now, it's really crucial to know that exoplanet scientists assess planetary habitability using similar tools that climate scientists here on Earth use to simulate and understand the changing climate of our world. So we use energy balance models, radiative transfer models, photochemical models, and even very sophisticated 3D general circulation models. And the real expert in the room about this kind of work is Emily. This is what her PhD thesis is about, simulating potential habitable world observatory targets and understanding what we need to look for in order to identify what they're like. Why do we need to run all of these different simulations? Why do we have to do all of this guesswork? It's because we recognize that Earth has been many different planets over its history. We know that Earth started off in this volcanic, hellish state. We actually call this eon of Earth's history the Hadean eon, after the Greek god Hades. Some people think that early Earth would have appeared purple because of the photosynthetic pigments of the earliest kinds of bacteria that would have eaten sunlight, photosynthetic bacteria. They would have appeared purple. The geologic record shows us that Earth has gone through numerous snowball phases where glaciers descended all the way from the poles close to the equator, potentially all the way to the equator. And today, our planet looks like this, the blue-green marble that we all know and love. But there's a beautiful contradiction with Earth. Not only is it so many different planets throughout its history, but it's also just one of many potential evolutionary trajectories that an Earth-like planet could take. Different initial conditions, different tilts of the planet, different star that it orbits, whether or not it has a moon, whether or not certain kinds of life forms happened to evolve on that planet, and when they did, will change the outcome of an Earth-like planet. And so Earth is many different planets, and also just one single trajectory out of an ensemble of possible trajectories that we need to anticipate. And so there's a brilliant quote by my colleague Jonathan Lunine in his astrobiology textbook. He writes, "The Danish prince Hamlet in Shakespeare's play of that name admonished his friend Horatio that there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Well, today, we might instead warn ourselves of the likelihood that there are more kinds of Earths in the heavens than are dreamt of in astrobiology. And so it is our job to dream those planets we haven't dreamed up yet in our computer code so that we can go and hunt for signs of their habitability and their life when we build HWO. Many exoplanet astronomers will tell you that we are looking for Earth 2.0. And one of the main takeaways that I want you to have from this talk is that Earth 2.0 is not a literal copy of the Earth. We're not looking for the place that we're all going to run to after we wreck our home planet. Instead, Earth 2.0 is a revised concept of what Earth-likeness is. Again, we only have one example of what an Earth-like planet can be and do. And it may be actually a much wider spectrum of kinds of worlds than we see right here at home. So astrobiologists try to break down this massive problem into sub-problems. The questions that astrobiologists like to ask are, how do lifeless planets transform into living ones? How do biospheres entwine themselves with geospheres? What are unique and universal features of living worlds? And even, can intelligent life learn to live sustainably as a steward of its world? Okay, I've done quite a bit of talking so far. I want to actually hand it over to you now. When I ask you to envision an Earth-like exoplanet, an alien Earth, what do you see? Feel free to raise your hand or just shout it out. Right here.
This is my first time coming to a lecture like this, so I'm going to sound very naive about the whole thing. My question, that what hit me is that are the scientists approaching it that another habitable planet would have like a twin of Earth? Isn't that unrealistic way of looking at life? Like, can't the definition of life be totally different than we might even imagine?
It could. And so it is our job to also try to imagine what those other kinds of life might be. Right.
And if that's the case, then aren't they looking at us?
Aren't they looking at us? Aren't the other lives out there looking back at us? Yeah, absolutely. Or, well, potentially. If they're out there and they have the same kinds of technologies of perception as we do.
They might have more.
And they might have more. Right.
We're assuming that we're the only ones looking.
We may not be. I like where you're going with this, but what does your Earth-like exoplanet look like in your head?
I'm thinking it's beyond imagination because most of the world is built on other things. The world used to be seen as flat.
Yeah. Some people still think it is.
So until it was accepted,
Right.
and the idea of evolution wasn't that long ago that it wasn't accepted.
Exactly.
So we move very slowly in our sense of imagination out of fear of the unknown.
Okay, right. I completely agree. And I think it is our job to try, nonetheless, to imagine beyond what we have here so that we can widen our scope. And we may not cover the entire scope, but at least we'll do a little bit better than looking for exactly Earth's twin.
So right now, as an astrophysicist, this is what you do is you've already accepted that there's probably more than just us, and that's too egocentric to think that.
Yes.
So that's like baby step. That's crawling. That's not even crawling. That's being a woman.
We are trying to move as fast as we can, and it is too slow nonetheless. Yeah, thank you. There's a hand back there. What does your Earth-like exoplanet look
I have a question.
like? Okay.
So photons take time to travel, right?
Right.
So if we look with our telescopes far, far away, then we might see like an Earth-like planet, but in an early stage.
Right.
So then how do we know if that planet will become an Earth-like planet?
Well, that's why we have to widen our scope. I showed you that timeline of Earth before. We can simulate what Earths would look like throughout their entire history. And we even need to step outside of that history to understand alternate histories to try to capture those planets as well. That's a brilliant question. Excellent. Does anybody ever pretend Earth-like planet in their head? I see you waving over there.
With water in it, lots of water.
Lots of water? Okay, very good. How about yours?
I was gonna say the same thing, like either ice or for water, but that contradicts his question, because then it could just look like a rock at first.
Isn't that so interesting? Isn't that so interesting, right? Is water required? I don't know, maybe. What do you think?
Like similar mass or size, basically. I feel like that really influences the geosphere and the biosphere that's present on here, and then kind of be a similar thing if there was another like planet like that.
Absolutely, similar size or mass, yes.
We are looking for an Earth-like planet
Right,
to host Earth-like life.
maybe.
If life is not Earth-like, we don't need Earth-like planet.
Oh, yeah, then we go look at all the other planets. Right, okay, I like where you're going, okay.
And yeah,
I was gonna say, like, on top of like similar mass, it could be similar, like the quantity or ratio of elements. maybe.
Okay, yeah, absolutely. Similar quantity or ratio of elements over here.
I think Earth has been through a lot to bring life, and so whatever we find probably also has been through a lot, and it's not a very stable place. It's a place that changes and can change, and there's lots of factors affecting it.
Okay,
So, like, something that has been through a lot.
been through a lot and has survived nonetheless. Yeah, Kat.
I think we could look for a planet that's on a tilted axis that has obliquity and
Okay.
has seasons as a result. And I think we could also look for a planet that's green or purple, since life on Earth, plant life anyway, is green, and those early bacteria were purple. We could look for those colors.
There's a shout out for seasons. I like that. In the back over there.
Right, similar appearance.
Similar appearance, right? Can we take a picture of the planet? Right.
If there is life on that planet, they probably have already started putting junk in space.
Oh, their junk. Looking for their junk. I love it. Yeah.
we've got two from online.
Oh, you got two from online. Go for it.
One is from Bettina, who says, considering the ability of extremophiles to thrive in environments that would be considered inhospitable to most Earth life, should we expand our definition of habitable zone and also look for planets that are unlike Earth?
Yeah, expanding our definition because of the extremophiles that we know can occupy extreme environments. One more from online.
And then Zoe said a temperature range similar to those that we have found extremophiles in on Earth.
Temperature range that encompasses all the extremophiles. Yeah, great. Let's take two more. You and then you.
Well, life in the deep oceans, in geothermal vents,
Oh.
doesn't require sunlight.
They don't need sunlight.
So people think you have to have a star, like sun, maybe you don't need a star.
Yeah, and indeed, most stars in the galaxy are not like the sun. So that widens our scope. Okay, last one right here.
So if we find a planet far away, then we'll have to go there with a spaceship. But if by that time the orbit is on the other side, then we'll go.
Whoops, we've missed it. Luckily, we have very good colleagues who are good at doing orbital dynamics calculations. And they'll make sure that when we get to the planet, it has also gotten to the same place. And that's actually how we go to Mars and things like that. So maybe you can grow up one day and be that person to make sure we don't miss our planet rendezvous.
Can I give you two more from
Okay,
online?
okay, two more from online and then we're gonna cut off. Yes.
Eric has, perhaps planets can host different types of life,
Mhm.
not just looking for humans, planets, animals, etc.
Yeah,
And then Gugrat said pressures that allow three states of matter, whatever that matter might be.
oh, I like that. Yeah, okay, I like the abstractifying that we've done here. Well done, everybody. That was a great discussion. Let me tell you about what scientists tend to think about when we define an Earth-like planet. And you'll see that a lot of this has echoes of what you've already discussed. So you're really thinking like scientists. An astronomer might say that an Earth-like planet is a planet of a certain mass, radius, and density, right? I think somebody said something along these lines. A geoscientist, on the other hand, might be interested in what the interior structure or mineralogy or elemental composition of that planet is. An astrobiologist, of course, is very concerned with the atmospheric state of the planet, whether or not it could host oceans, does it have a stable climate? And then a biogeochemist might say, what are you talking about? If you don't even have a biosphere, then you don't have an Earth-like planet at all. So in this portion of the talk, I want to submit to you that perhaps Earth-like planets or Earths should be defined by relational rather than intrinsic properties. And this may not seem so radical once I remind you that the International Astronomical Union's definition of a planet contains two relational criteria and only just one intrinsic criterion. So that intrinsic criterion is that the planet must be in hydrostatic equilibrium. All that means is that it has to uphold itself into a round shape based on its gravity. The other two criteria, that it must orbit the sun and must have cleared its gravitational neighborhood, are relational criteria. They don't have to do with the planet itself, but its relationships to the rest of the bodies in its solar system, right? So what do I mean by Earth being defined by relational properties? I mean to think about the systems that have emerged on that planet and how they have coupled to one another in diverse and intricate and self-promoting ways. So for example, a planet might have a water cycle. It may have water on its surface. Water actually enables and prolongs plate tectonics on a terrestrial planet by hydrating the crust. Plate tectonics helps liberate heat from the interior of the planet and may play a crucial role in driving and maintaining the planet's magnetic field. And a magnetic field shields the atmosphere from solar wind, enabling that planet to maintain what's called the carbonate silicate weathering cycle, which is a planetary thermostat that enables the existence of liquid water on the surface. Right? So you see this dynamic ecology of geological forces conspiring to maintain some kind of planetary homeostasis or balance. And in this relational framework of what an Earth-like planet is, we can see life as something that emerges on that planet and then embeds itself in this web of interactions to increase its complexity, yes, but also to help maintain self-promoting feedbacks through interactions with its environment that feeds back upon itself and interactions with itself as well. Let me give you a concrete example of this in action. My favorite example, believe it or not, has to do with woolly mammoths. So woolly mammoths are a now extinct species of animal that used to roam all across Siberia. And did you know that there is a connection between the existence of woolly mammoths and the cool temperatures of Earth's ice age? So here's how it goes. Woolly mammoths, through the kinds of nutrient cycling that they perform, actually enable and promote a certain kind of biome, Arctic grasslands, over a different biome, say, of forests. Woolly mammoths, through stomping on the ground, on snow, actually enable there to be a stable permafrost by compacting that snow into ice. The existence of Arctic grasslands also promotes stable permafrost, because when the grass grows in the summer, it actually insulates the permafrost, stopping it from melting during the warmest months of the year. The Arctic grasslands are a type of biome that is really good at creating biomass from the CO2 in the atmosphere, drawing down the CO2 in the atmosphere, therefore maintaining those cool temperatures. And the stable permafrost does similar things by raising the reflectivity of our planet's surface, meaning that Earth doesn't absorb as much sunlight as it otherwise would if it were covered with dirt or forests. And therefore, it doesn't heat up as much, maintaining the cool temperatures. And the cool temperatures, therefore, provide favorable conditions for these woolly mammoths to thrive. That is until humans came along. About 50,000 years ago, we hunted woolly mammoths all the way to extinction, which destabilized Arctic grasslands and the stable permafrost in Siberia. Once you lose the permafrost, the reflectivity of that surface goes down, Earth absorbs more sunlight. And once you no longer have the grasslands, we can now liberate and release all of that carbon back into the atmosphere. And this raises the temperatures of our planet to a climate that is now dangerous for humans. And for evidence of this, just look at the tragic and devastating fires that are currently blazing in LA. Now, whenever people talk about climate change, they always talk about the last 250 years since the Industrial Revolution. It's absolutely true. That has been a major driver of climate change. But humanity has actually been doing climate change for the past 50,000 years, ever since we caused the mass extinctions of these giant macrofauna. So we might actually, and scientists are arguing that the Anthropocene, the geologic epoch that talks about and denotes human activities on our planet, should actually begin roughly 50,000 years ago. Now, of course, we cannot blame our ancestors for having hunted the woolly mammoths to extinction. They had no idea what they were doing because they did not have this complex networked picture of Earth's ecology, largely because they did not have the right technologies of perception. In addition to building telescopes that view outer space, space exploration has given us a fleet of satellites that are Earth sensing, that understand our warming climate, our sea level changes, the pollution in our atmosphere. They give us a kind of planetary sapience. We are the part of Earth that has come to understand itself. Now, we're not the first species on planet Earth. Yes?
Sorry, quick question. Your previous slide, what was the second council?
Those are the differences. That's a great question. Those are the differences in the orbital, like how long it would take for one of the satellites to get to that other satellite's position. This is a constellation of satellites called the A train.
And they follow the same
They follow each other. Yeah, great question. So we're not the first species to on Earth to radically alter our planet's climate, but we are the first species on Earth that is aware that it is causing climate change. And with great knowledge comes great responsibility. And one question that weighs on my mind these days very heavily is whether or not we can reorient ourselves, our activities, our society, our civilization toward planetary homeostasis. So we've gone all the way from telescopes to environmentalism. And you might be wondering, what does this have to do with astrobiology and our search for life in the universe? Well, it actually has quite a bit to do with that, mainly because one of the sub-questions in astrobiology is whether or not this cartoon is true. Right? So this is a play on the classic habitable zone. Usually it goes, Venus is too hot, Mars is too cold, and Earth is just right for life. But maybe, who knows, maybe actually this version of the habitable zone is the pervasive situation across the cosmos, that there are planets that are too hot, too cold, and too dumb to survive for a long time. I would wager that the lifetimes of planetary civilizations, remember that L variable from the Drake equation, isn't just a single number or a normal distribution of that number, but probably a bimodal distribution, one with two humps, one a pileup of civilizations that are very short-lived, and another pileup of civilizations that quote unquote figured it out. Now, I don't know anything about the numbers in this graph. That's why it's very unlabeled. I don't know whether this hump is actually much larger than the other one. I would like to think and hope that it would be. I don't know how short a short-lived civilization is, and I don't know how long a long-lived civilization is. Nonetheless, I think there is good reason to logically argue that the L variable has a bimodal camel-humped distribution. Now, what does figuring it out actually mean? Figuring it out, I believe, one of the first steps to doing so is acknowledging and understanding how we are an integral part of nature. We are all brought up in this society implicitly understanding and being taught that we are external. Humanity is external to nature, that we can take and extract as much as we want from the natural world and impose our will on it to make it do whatever we want to do. When in reality, Earth system science is teaching us that the situation looks a lot more like this, that we are a powerful part of the entire web of nature. We can make a big influence on it, and we are. But what goes around comes around. The harm that we inflict on our ecosystems and our environments will come back to bite us as well. And actually, indigenous knowledge systems tend to hold this kind of picture and preach this kind of picture. And I think there's a great deal that we have to learn from the First Nations and the indigenous folks of the Americas. Figuring it out, I think, also involves potentially recasting this Arthur C. Clarkeism that reads, any sufficiently advanced technology is indistinguishable from magic, to this version. Any sufficiently advanced civilization is indistinguishable from nature. I think if we took this casting, we might look for alien civilizations, for quote unquote alien intelligence in a much different way from our current techno-signature based approach. And finally, part of figuring it out is also figuring out how we stand in relation and treat other extraterrestrial phenomena and environments. And so in this last portion of the talk, I want to tell you about astrobioethics for a new era of planetary exploration. This is work that I'm doing in collaboration with Emily and two of our brilliant colleagues, Julia DeMarinis and Chelsea Harmon. So As you all know, human spaceflight is entering a commercial renaissance due to the rising influence of private space corporations. Our access to outer space has never been greater, thanks to the efforts of entities like SpaceX and Blue Origin. So Emily and I believe that it is imperative to do the hard work now of developing ethical guidelines for the exploration and treatment of extraterrestrial phenomena. Why? Because we have an obligation to respect that which is morally valuable in outer space, which begs the huge unanswered question of what actually constitutes moral value in space. So in philosophy, the concept of intrinsic value underpins moral and ethical discussions, where intrinsic value is differentiated from instrumental value, in that intrinsic value describes an object's value for its own sake, whereas instrumental value describes an object's value as a means to an end for something else. So for example, a human being is tremendously intrinsically valuable, but money is only instrumentally valuable because it gains its value through being in the context of human-human exchanges. Crucially, any given entity can express multiple forms of value at once. A tree can be intrinsically valuable because it's a living being and have instrumental value as a source of lumber and wood and shade for us. Now, there's a great debate in philosophy about where to draw the line between things that have intrinsic value and things that only have instrumental value. A lot of people would pin this division at life. Others might pin it all the way on the side of humans because of our supposed uniqueness in terms of sentience, rationality, and culture. But I think this one-dimensional hierarchy of moral value misses the interconnected webs of interactions and relationships that we've just been talking about. After all, we rely on trees for the oxygen in the air that we breathe. We rely on our gut microbiome for the functioning of our bodies. We rely on the concept of money for the functioning of our societies. And all of this relies on the geology of our planet for its long-term habitability. So in our work, Emily and I are advocating that we also see how relationships generate value. So let's go back to our woolly mammoth example. Woolly mammoths are charismatic creatures with tremendous intrinsic, innate value for just being what they are. But they gain another emergent level of value due to the fact that they play a vital role in this ancient ecosystem where they actually helped affect planetary climate. So we've coined this new term, systemic value, where systemic value is derived from relationships that create systemic integrity, regenerative ability, or future evolutionary potential. And we've drawn up this huge, diverse taxonomy of different kinds of moral value that we can see in space. And I don't have time to go through each and every one of these different axes and planes here tonight, but essentially what we're advocating for is a multiplicity of moral value that allows us to see how different phenomena, environments, and potentially alien life are valuable in different ways. So to summarize that, the multiplicity of moral value means that we can see how different phenomena can be intrinsically valuable for different reasons. And just as we don't devalue the Earth for failing to be a gas giant or a star, similarly, we shouldn't devalue other planetary phenomena simply because they fail to be like Earth. In planetary science, I hear very often things like Mars is a failed Earth. But what if instead we took the perspective that Mars didn't fail at becoming Earth, Mars succeeded at becoming Mars. And we must treat Mars with respect on its own terms. Okay, to wrap up, let me share with you the most brilliant night sky that I've ever seen. This was at the bottom of the Grand Canyon in Arizona on a backpacking trip. And it was just amazing. Shielded from light pollution by both sides of the canyon. You could see the Milky Way stretch from one side to the other. And looking up at this and just being astonished with my own naked eyes about how beautiful the cosmos is really cemented in me this belief that we have so much to learn from the universe. We have so much to learn about our strengths, how they are mainly derived from our relationships, both obvious and subtle. We have so much to learn about our fragility, how all that separates us from the void is about 50 kilometers of gas, and how we need to take care of that gas. We have things to learn about where we came from. Astrobiology, the origins of life, teach us that we come from the humblest of beginnings, single-celled life forms swimming in Earth's early oceans. Doing science also teaches us about who we are, right? And it's taught me that we are incessant explorers, inevitable dreamers, and persistent storytellers, as well as who we must become. You know, the search for alien life is not something that we do because we want instant gratification. It might take years, probably decades, maybe even centuries, to find definitive evidence of alien life. And if we are to give ourselves, our civilization, the best chance possible to actually make that discovery, then we have to become the hope that we want to find in the cosmos. We have to become one of those planetary civilizations that figured it out. And finally, the cosmos teaches us about our planetary belonging, that this is home, that this pale blue dot is our perch from which we peer out into the cosmos and learn about who we are. Thank you very much.
Thank you so much, Mike. Can you take a few questions?
Absolutely.
Start up there.
Hi.
Thank you. The Drake equation in 1961, you mentioned, did Drake come up with an estimate himself? And if he did, was it close to the 1964 Star Trek writer's 3 billion? And basically my question is, the 40 billion today's estimate, how does that compare with what the estimate was in 1961?
That's a really good question. I think if I'm remembering correctly, that Drake's estimate was something like 10,000. I don't know that for sure. Emily's nodding, so I'm slightly more confident now. And I think the main reason for that is because he found that all of the terms leading up to that L canceled out. They all multiplied together to be about 1. And so it all hinged upon what that last term was, the lifetime of a planetary civilization, and he took that to be about 10,000 years, based on how long human civilization roughly has been around. So it was quite a bit smaller, I think, than the 40 billion estimate that I showed. But the 40 billion was only for those first 3 terms multiplied together, right? So it forgot about, you know,
sort of the more certain size.
Exactly, right.
So how does that compare with like the 3 million from Star Trek? Would that be like a really forward thinking?
Yeah.
It seems silly now, 10,000 factors smaller.
Yeah.
Is it?
You know, what's most impressive to me about Star Trek was that it was written 3 decades before the first exoplanet was found. Back then, they didn't know whether or not all the stars in the night sky, if any of them had planets going around it. They had good reasons to believe that they did because our star had planets going around it. But what Kepler, TESS, and the other astronomical observatories that have discovered all of these planets has taught us is that Star Trek's expectation that there really would be a new planet to go to every single week was actually true, right? And so I think that the 3 million guess, it had to be there because it had to be consistent with the universe that was depicted in Star Trek, that there was a new alien planet to go visit every week, but they had no idea. It could have been nothing. And it turns out that we do live in a universe that seems to be teeming with planets. Right here.
So humans, we need perfect amount of gravity, right? So if it's a little bit lower, we'll float up. If it's a little bit too much, we'll rush down. So the possibilities of finding an Earth-like planet that could sustain human life is very low because it's perfect amount.
Right, and that's one of the reasons why we think it would be so difficult to go and live permanently on Mars. Right? Mars's gravity is roughly a third of Earth's. Yeah. And astronauts on the International Space Station these days are studying how changes in gravity affect human life and our well-being. They're finding all kinds of strange things happening to the people that go up there. Right, everything from we're just talking over dinner about bone loss, right? Because you no longer have to fight the gravity to keep yourself up, so you lose a lot of that bone mass. To the deformation of your eyeballs, to the radiation damage to your genome. So there's all sorts of things. You're absolutely right. And I think that's why we really need to make our stand here on Earth. This is our home. This is what we've evolved to thrive in. So we have to take care of it.
A couple of questions from online.
Okay.
There's one, when you talked about the relational definition of planets.
Yeah.
Bettina was asking that since the IAU's definition doesn't include rogue planets, will there be a evolution or a revising of the definition?
Yeah, so the definition of a planet doesn't even include exoplanets, because if you notice, the second criterion was that it must orbit the sun, and all exoplanets by definition do not orbit the sun. So technically they're not planets, which sucks. I think we should revise the definition to say orbits a star. Rogue planets that Bettina was asking about. What is a rogue planet? It's a planet that doesn't orbit any star. And there are actually estimates that there are, billions of rogue planets out there, potentially more rogue planets than there are stars, because as planetary systems form, this is a whole other lecture, but they form very chaotically, and they very often will eject material out of their solar system as planets get too close to one another. And so there are probably very many quote unquote rogue planets just wandering the gaps between stars. And we don't know if they're habitable. Some people say that there are certain conditions where rogue planets can be habitable for the kind of hydrothermal vent-like life that one gentleman brought up earlier, because they don't need sunlight to maintain themselves. But it will be very hard to study rogue planets, because most of our studies of exoplanets come from how they interact with the light from their parent star, right? That's how we get to know about their chemical compositions. For rogue planets, that kind of measurement is simply impossible.
And then the next two I'm going to ask you together so we can go back to some of the questions in person. Because I think the first one is a little bit with the HWO, but it was, if you could fund one dream astrobiology experiment, no matter the cost, what would it be? And then the associated one is, how long did it take you to become such an amazing astrobiologist?
Okay. My dream astrobiology experiment would be to run a large-scale, multi-billion-dollar origin of life experiment. We actually don't know how life began on Earth. And so far, origin of life experiments last on the order of years, just because that's how long graduate students have to graduate. But who knows? The origin of life could have taken millions of years. And so in order to speed up that process, we have to run like a large hadron collider scale origin of life experiment, where we're trying all different kinds of chemical combinations forced by different environmental factors. I think that will really speed up research in that particular tentpole of astrobiology, and will actually help us understand better the conditions on which we can expect life to be out there in the universe. Because there's a big difference between a planet being habitable, which means that it can sustain life, and a planet that is genial. That's my word for can produce an origin of life. There may be plenty of habitable environments out there, but if none of them have the conditions for an origin of life, then they're just sterile. And so in order to prioritize our hunting for planets with life, we may need to know something more about the origins of life itself. Okay, yeah, back there.
What about Earth-like moons? If there's a big focus on planets, then those you might have heard of Europa, one of Saturn's moons, and it's said to be maybe Earth-like due to water being under the ice.
What about them? That is a whole other lecture as well. But I love Europa. It's one of my favorite bodies in the solar system. And you're exactly right. We think that there are Earth-like conditions at the bottom of Europa's ocean, very similar again to these hydrothermal systems that are just teeming with Earth life, feeding off of the chemical gradients there, not sunlight. And there's a mission on its way right now called Europa Clipper that is going to visit this moon and take readings that will help us understand its habitability. So I encourage all the Europa fans in the audience to go and search up Europa Clipper and follow its highlights. Okay, down here.
Yes, one of my favorite episodes of Star Trek was the Creature the Horta.
Yeah.
And that's how we should approach protecting our planet Earth, because they thought this creature wasn't a creature.
Right.
It was protecting its eggs, and Spock had to communicate with that creature to save it from extinction. And I think that's how we have to look at life on other planets of life. We have to learn that we have to respect it, what we discover, and not let it go extinct. That's what's happening here.
I love the episode. The Devil in the Dark is the title, with the Horta, which is a silicon-based life form. It's basically like a lava rock creature. And they didn't understand what it was at first. They just perceived it as a monster. But they found out that actually was just a mother trying to protect its eggs. And once they discovered that, they granted it a whole bunch of intrinsic value and respect based on their understanding of it as a living creature. And that's the kind of thing, exactly, I completely agree. We need to be open enough as astrobiologists to notice life that is not exactly like life here on Earth, and then be open enough in the ethical perspective to treat very different life from us with that kind of respect. And honestly, we don't do a very good job of that even with our own Earth life here on our planet. So one of the hopes of our Astrobioethics project is that even if we never discover alien life, which we need to treat ethically, hopefully by revisiting our ethical considerations with regard to that imaginary alien life, will actually improve the way that we treat life here on Earth. Yeah.
Question along this line. I love everything space, but as you know, Starship is taking off on its 7th flight on Monday, and the goal of Elon Musk is to quote unquote colonize Mars.
Yeah.
What if there's potentially, bacterial life still on Mars now? And like you said, we go there and then we, like what we do best, we kind of spoil it because of expansion or colonization of another world. Well, what's your thoughts of that multi-trillion-dollar push to colonize Mars? Because that's a real thing now, or it will be.
This is a real concern of us in the astrobiology community. What you're getting at here, we call planetary protection, right? So we don't want to spoil a potential alien ecosystem with our own life, right? We don't want to go to Mars and bring life accidentally for a scientific reason as well, which is that we don't want to go there, find life, claim that we found alien life, and then have only done PCR on like Earth bacteria and that hitched a ride there. That would be really bad. But we also do, for these same ethical reasons, one of the things we're trying to do is raise awareness of the intrinsic value of very simple systems as well that have eked out an existence on Mars and what considerations we need to give them. I really think that we need to elevate our understanding, our ethical considerations because of this push to go to Mars. And also, we are trying to beat Elon Musk there with robotic missions. There's something that we're involved in right now. The Search for Life Science Analysis Group is trying to design one last ditch experiment to send a robotic mission to Mars to go and look for extant life before somebody inevitably spoils it. And so that's an active concern of NASA. Over here.
Regarding your astrobio ethics, everybody's really concerned about AI and the ramifications of the future of AI and how it's going to disturb us. What about actually one day shining that beam, looking at the radiation coming back from some exoplanet and saying, wow, there really is life there. And then you just disseminate it across the world and say, we found life somewhere else with no, isn't there an ethical consideration? I'm reminded of the movie Contact by Jodie Foster, where basically the planet goes nuts and we all start demonstrating and jumping off buildings. Is that part of the ethics?
That is an element of the broader concern of the astrobiology community, is how do we do proper science communication? There's a workshop that's going to happen in April of this year at the University of Arizona's Astrobiology Center, centered exactly around that question. How do we relay what are the best practices for us scientists telling the public that we found something interesting? We actually don't really have protocols for that yet. Although the SETI community has thought a little bit more deeply about it than astrobiologists have. And so hopefully we'll learn a little bit from that. Yeah, but it is a really big concern. I wonder how people will react. I mean, how would you react if you saw a headline tomorrow that scientists have discovered evidence of alien life? And does it change if it's just a bacterium on Mars or a signal from an alien civilization? How would you think about that yourself? Maybe you don't care, right? The majority of Americans, I believe, the last poll was that they think that aliens have already visited Earth, right? And so like maybe nothing will happen. I don't know. And that's one of the biggest questions in my mind as well.
That'd be the most awesome.
That connects with one of the online questions, which is, could it be possible that we are completely alone and life happened here, just happened, and it's a hypothetical, but what if we're looking in the dark?
It's certainly a possibility. We can't rule it out yet. a lot of people ask me, Mike, do you believe that there are aliens out there? And I say, as a scientist, it doesn't matter what I believe, right? My job is to go and get the data, and the data will tell us, right? And so that's all we can do. There may not be anybody out there, but that's still a really profound discovery and should make us cherish our own existence all the more.
We take a couple more questions here.
Okay, sounds good. So two more, one here and one here. Okay.
Would you say that data or that holographic doctor from Voyager are life forms?
Yeah, okay, good question. So in Star Trek, there are some artificial life forms. Data from the Next Generation is an android. On Star Trek Voyager, there's an emergency medical hologram that gains sentience. And I think that those entities are life, and something that we have to wrestle with increasingly as AI gets more and more sophisticated is whether or not we are creating life, a second instance of life here on Earth in our technology, right? Just as we have to be open-minded to other forms of chemical, biological, exobiological life, we should also be very mindful of the fact that life may not need liquid water and organic substrates, but could potentially exist in machine form as well. Right? We talk about computer viruses, right? There's a huge debate in biology about whether or not viruses are life, but we already made computer viruses. So what if we made artificial life forms here on Earth? That conundrum is very similar to trying to identify and being open-minded enough to try to find alien life of a different chemical substrate as well. So yes, I would think of them as life forms in a science fiction sense. That is actually a very pertinent question for what we may see in the next few decades. Last question.
So when a star gets, when a planet gets big enough, it becomes a star, right?
Okay, when a planet gets big enough, does it become a star? Is that the question?
No.
Okay. Just to lay out. What's the question?
But if it does become a star, then how does it become a star? Does it get on fire?
Yeah. Okay. So when a bunch of gas and dust self-gravitates into a round body, depending on the mass of that stuff, it will create different kinds of objects. Okay? So Earth is mostly rock. Jupiter is a rocky core, but that core got so big, roughly 10 times the mass of Earth, that it was able to gravitationally collect a bunch of gas on top of that. And that's why Jupiter is a gas-giant planet. Some things have so much gas that they collect and then they start to do nuclear fusion in their cores because of the overlying pressures and temperatures in their cores just that high. When that ignition happens, then we call it a star. Okay? Cool. Excellent.
Well, I'd like to thank Mike for an amazing presentation. There's a few things I took away from this. The first one is a bit on the humor side. When I suggested that if you ask a question, we'll make it up. And well, Gene Roddenberry obviously embraced that concept. Going back to my days of McGill way back in the 70s, I was in geography. And my first professor gave me a research job. John Bradbury told me that BS baffles brains. So that was just on the humorous side. I don't know if anybody's read Andy Weir's, I think it was called The Artemis Project, his book. And if you read that, that sort of reflects of man running into an alien life form, which they didn't understand at the beginning. They thought it was going to destroy them. But when it turned out, the alien saved the main character, bringing him onto their planet and building a sphere where he could survive. And he was a teacher. And the book ends with him teaching that life form about mathematics and what was out beyond them. So it was just interesting that the two came together in a fictional book, or maybe nonfiction, who knows? And finally, I invite you in our own little way to, when you go outside, look up, look at the stars, and just wonder what's out there. And if you get to a location like Woolly Woods or away from the city, look up and just be amazed what you see. And just with an open mind, wonder what's out there. We don't know, but who knows? And if you see a streak of light going across, wave, they may be looking at us. So with that, I just want a few little things for our speaker to take away. A little certificate of our appreciation.
Thank you.
And whatever life planet is out there, I really hope they have coffee. So, speaking of coffee, we have coffee here and some cookies, substance of life. Help yourself and let's have some conversation.
Thank you, everyone. And there are some outreach materials here as well as refreshments. Please help yourselves.